Imagine a place where there is nothing, no light, no sound, no matter, nothing. But wait, is there really nothing there? This is where the deepest, most mind-boggling question of the universe begins. Because physicists tell us that what we call emptiness is not empty at all. It is invisible but real, silent but powerful, seemingly non-existent but full of energy that determines the fate of the universe. Invisible fields, vibrating even in the most desolate corners of space. The momentary dance of virtual particles, and the mysterious quantum void from which everything may have been born out of nothing. So, what lies beyond this invisible veil? Perhaps the greatest secret of the universe, everything hidden within nothingness. 1. Space is not empty. What is the quantum vacuum really? What we call space is not the nothingness we imagine. Modern physics reveals that space is actually filled with an invisible, yet perceptible, quantum sea. Although this quantum vacuum appears to be an environment where nothing exists according to classical physics, it is actually a fundamental level where vibrating energy fields boil. Space is like an invisible skeleton on which all reality in the universe rests. Within the quantum vacuum, virtual particles constantly appear and disappear. These are temporary entities that we cannot directly observe, but whose physical effects we can measure. In other words, space is an invisible, yet active stage. On this stage, matter and energy constantly emerge and vanish, much like actors preparing behind the curtain in a theater. This quantum fluctuation provides a fundamental clue about how the universe is shaped. Matter, energy, and even time are built upon this dynamic foundation. Within the void, there is potential at every moment, for the apparent silence is actually a state of constant boiling and creation. This perspective helps us understand the universe not as a static structure, but as an ongoing process of creation. The idea of the quantum vacuum is powerful enough to completely transform our understanding of physical reality. We now know that nothing does not exist. Even at the very foundation of the universe, there is some kind of invisible structure, a vibration, a sea of possibilities, and this sea could be the source of everything. Perhaps the void is much more full than we ever imagined. By the way, if you like my video and subscribe, that's the most effective way to support me. 2. How do virtual particles appear and disappear in an instant? In the quantum world, strangeness is commonplace, and virtual particles are the main actors in this strangeness. These are temporary entities that do not exist, like real particles, but emerge for a brief moment using borrowed energy. They appear suddenly, create physical effects, and then disappear without a trace. We cannot observe them directly, but we can measure their effects experimentally. This temporary birth and disappearance is a direct consequence of Heisenberg's uncertainty principle. According to this principle, there's uncertainty between energy and time. A system can borrow energy for a very short time and use it to create a virtual particle pair. However, these particles quickly annihilate each other in a way that does not violate energy conservation. This cycle creates the invisible dynamism of the void. These particles are not merely theoretical fantasies. Their existence has been detected through experimental results, such as the Casimir effect. The attractive force between two metal plates arises from the creation and annihilation of these virtual particles. Even Hawking radiation is formed when some of these particle pairs emerging at the edge of black holes fail to fall into the black hole. This effect allows black holes to slowly evaporate. The existence of virtual particles shows that space is actually an ocean of energy. These particles are not just temporary shadows. They carry powerful clues about how the universe works at the micro level. Without them, some of the physical laws we see today might not hold. The quantum vacuum is a far more dynamic and creative stage than previously imagined. 3. Why do quantum fluctuations never stop in the vacuum? In the quantum world, nothing is completely static. Even a system at 0 point can never be completely motionless. Quantum fluctuations are based on this principle. Energy constantly vibrates in space because absolute stillness between energy levels is impossible. These fluctuations are an essential part of quantum fields. The constant nature of quantum fluctuations stems from Heisenberg's uncertainty principle. Energy and time cannot be measured precisely at the same time. This means that the system must allow for momentary energy fluctuations. Space, therefore, does not have zero energy, but rather 0 point energy. In other words, it is not stationary, but rather constantly in motion. These invisible vibrations may have led to enormous consequences in the first moments of the universe. Immediately after the Big Bang, these oscillations may have laid the foundation for galaxy formation. Even cosmic microwave background radiation is a remnant of these early vibrations. The effect of these first whispers in space is hidden in the complex structure of the universe today. Quantum oscillations show that the void is not absolute nothingness, but a creative ground filled with possibilities. This invisible movement within nothingness can be thought of as an unconscious dynamism underlying all existence. Perhaps the universe is nothing more than a symphony of these vibrations. 4. How can energy exist, even where there is nothing? In the intuitive world of classical physics, nothing truly meant nothing. But quantum physics shattered this understanding. Even a space where no particles, waves, or light exist can possess energy. This energy is called 0 point energy, and is one of the building blocks of physical reality. Emptiness is not the opposite of nothingness. Rather, it is the fundamental level of energy. This energy demonstrates that zero is unattainable in the absolute sense. Not even a single particle can exist with zero energy, because quantum laws do not allow it. Similarly, even if there are no particles in space, energy still vibrates there. This is an important finding that shows the universe can never be completely static. This idea has been experimentally confirmed by the Casimir effect. When two metal plates are brought together in a vacuum, the difference in virtual particles between them creates a force. This force concretely demonstrates that there is energy in the vacuum. This is not just a theoretical game, but a physically measurable reality. This understanding also explains why the universe could have emerged suddenly from nothing. Perhaps the universe arose as a result of an energy fluctuation in the quantum vacuum. In other words, space is a starting point charged with potentials. This ground filled with invisible energy is the purest, most fundamental state of reality. 5. Did the universe really emerge from nothing? The birth of the universe has been one of the greatest questions in human history. The question, can something come from nothing, is not just a philosophical debate. It is now a subject of experimental and theoretical research that modern physics is directly addressing. While traditional belief systems and classical physics assume that the universe or everything must have a cause, quantum physics has introduced a concept that overturns this understanding. What we think of as nothingness is not absolute nothingness, but a quantum ground filled with potentials. This ground is an energy sea that appears empty, and the quantum fluctuations in this sea can transform into real particles at the right moment. This idea is revolutionary in explaining the beginning of the universe, because it suggests that the universe could have emerged from within itself, without resorting to an external creator or a first cause in the classical sense. This view is supported by theories such as cosmic inflation and quantum cosmology. According to some theories, the universe may have emerged from an unstable point in the sea of energy as the product of a quantum fluctuation. This is not a process arising from nothingness, but from the zero-point energy of the quantum vacuum. In other words, we are not talking about a classical sense of nothingness, but rather a level of existence that is invisible but has physical effects. In this context, what is referred to as nothingness is actually a creative field filled with energy and physical possibilities. This new perspective on the origin of the universe attempts to describe a before that is devoid of time, space, and matter. Stephen Hawking and some contemporary theorists argue that the universe came into existence with time, and that it is meaningless to speak of a time before time. This approach does not take us away from the idea that the universe has a beginning, but it changes the nature of that beginning. According to quantum field theory, the universe may have come into existence on its own, thanks to quantum uncertainties. This raises the idea that, in the classical sense, nothingness may never have truly existed, because even the smallest energy vibration in the quantum vacuum is not technically nothingness. Ultimately, the idea that the universe arose from nothing depends on how we answer the question of what nothingness is. If nothingness is not absolute nothing, which quantum physics says it cannot be, then the place where the universe arose is merely an apparently empty quantum field, and this field contains an immense potential that holds all possibilities, all particles, all times, and all spaces. The emergence of the universe may not be in an explosion, but rather the realization of a possibility. 6. How can quantum fields be real if they are invisible? Quantum fields define the deepest level of physical reality. However, we cannot see them directly, touch them, or even measure them in the classical sense. This contradicts the intuitive perception of the human mind, as we generally consider things we see or hear to be real. Yet modern science has taught us that invisible things can be just as real as visible ones. Quantum fields are among these invisible structures that form the basis of all material reality. Even particles such as electrons, photons, or quarks are actually energy concentrations that emerge in specific regions of these fields. In other words, the particles we see are nothing more than wave packets of the fields. The existence of these fields has been experimentally confirmed numerous times. For example, a quantum field like the Higgs field was discovered through the Higgs boson. But the Higgs boson was just a tiny glimpse of that field. The field itself is spread throughout all of space and exists everywhere. We don't observe these fields directly, but we can infer their existence by measuring their effects, just as we cannot see the wind but know it is there because of the swaying of trees. We understand quantum fields from the behavior of particles, their energies, and their interactions. Fields form the infrastructure of reality, and without them, the physical universe would have no structure. Moreover, the reality of quantum fields is not limited to the microscopic scale. It also manifests itself at the macroscopic level. Many technologies, from laser technology to semiconductors, MRI devices to GPS, operate through the direct effects of quantum fields. If these fields did not exist, none of these devices would function. Thus, even in our daily lives, there are traces of invisible quantum fields. Realizing that these invisible structures form the world we see is like a metaphysical enlightenment that challenges the limits of consciousness. Our prejudice against invisible things may question the reality of quantum fields, but science does not remain indifferent to the invisible. Criteria such as measurability, influence, and consistency clearly demonstrate that quantum fields are the most fundamental building blocks of physics. The fact that we cannot see them with the naked eye does not mean they are imaginary. The real fantasy may be believing that only what we see is real. 7. How does zero-point energy constantly vibrate in a vacuum? Zero-point energy is the lowest energy level a system can reach, but this does not mean no energy. Quantum physics shows us that no physical system can remain completely motionless at absolute zero. This is directly related to Heisenberg's uncertainty principle. Energy and time cannot be measured with absolute precision at the same time. This allows even the lowest energy levels of a system to exhibit small vibrations. These vibrations are called zero-point oscillations and are one of the most fundamental structures of the universe. Even empty space is not completely silent. At the microscopic level, it is constantly moving, rippling, and bubbling with whispers. This energy can even affect the existence of ordinary matter. For example, a small portion of the gravitational force between two neutron stars may be attributed to zero-point energy. Similarly, the Casimir effect is explained by the attractive force between two metal plates caused by zero-point energy. This experimentally measurable effect demonstrates that space is not nothing. Even though it appears empty, the invisible void is actually filled with constant vibrations. This is why the quantum vacuum is not nothingness, but a living fabric with continuous energy. According to some theories, zero-point energy may even affect the cosmological constant. In other words, this energy, which determines the expansion rate of the universe, is not limited to the microscopic world, but also manifests its effects at the macroscopic level. This implies that the overall structure of the universe is directly influenced by these infinite vibrations in space. This is why a possible connection between dark energy, one of the greatest mysteries of cosmology, and zero-point energy is being investigated. The fact that this energy level is not zero carries a very deep meaning. The universe has never been and will never be completely still. At the core of reality lies a constant turbulence, a wave, a potential. This potential could be the source of creation, change, and evolution. Perhaps what we call time is linked to the constant motion of zero-point energy. The universe's heartbeat may be silently but continuously pulsing with this energy. 8. Why is cosmic background radiation the echo of emptiness? Cosmic microwave background radiation is like an echo left over from the birth of the universe, approximately 380,000 years after the Big Bang, when the temperature of the universe dropped and photons began to be released. These radiations spread into space and are still measurable today. These radiations are considered to be the baby photos of the universe. However, when we delve deeper, this radiation is not merely an ancient remnant. It is also an echo of the first movements of the quantum fields, or the void itself. The cosmic background radiation is not just a glow emanating from the depths of space. It is the reflection of the vibrations that accompanied the emergence of time and matter, echoing into the present. The uniform distribution of this radiation in all directions across the universe is directly related to the homogeneous structure of space. However, within this distribution, millimeter-scale deviations reveal how galaxies and structures form. These small fluctuations explain how quantum fluctuations in space grew and transformed into massive structures in the early universe. In other words, even the silence of space disrupts its own symmetry, and this disruption lays the foundation for all the complexity we see in the nature of the universe. This echo born in silence actually shows that space is never truly silent, but rather a structure that harbors potential. The cosmic background radiation is being studied today with giant satellite telescopes, and the data obtained is contributing greatly to our understanding of the nature of space. The order and disorder in this radiation allow us to trace back to the quantum fluctuations at the moment of the universe's birth. In short, the first cry of space is still echoing today, and this echo whispers to us that space is not merely a field. It is a creation stage filled with time and energy. 9. Are virtual particles real or just a computational convenience? Virtual particles, which are frequently mentioned in quantum field theory, are defined as temporary entities that do not physically exist but appear in calculations. However, this definition can be misleading. Although virtual particles are not observable in the classical sense, their physical effects can be measured directly. For example, when two electrons approach each other, the concept of virtual photon exchange is used to explain the electromagnetic force between them. These photons are virtual because their energy and lifetime are limited by the Heisenberg uncertainty principle, existing only temporarily. However, this temporary existence is not merely a mathematical abstraction. It is the cause of observable interactions in the physical world. The existence of these particles cannot be experimentally proven because, by their very nature, they do not become real particles when measured. However, their effects are observable. In experiments such as the Casimir effect, the pressure difference created by virtual particles in a vacuum can be directly measured. This demonstrates that a non-classical entity can have an effect in the physical world. In this sense, virtual particles are like a bridge between physics and metaphysics. They are examples that prove the reality of the invisible and constitute one of the deepest mysteries of modern physics. The behavior of virtual particles can be thought of as similar to the temporary ripples of waves, like the peaks of waves that emerge from the depths of the ocean, appear for a moment, and then disappear. What is actually happening is an instability or temporary instability in the quantum field. This instability leaves temporary effects on physical reality. Virtual particles are the mediators of this transition. They are not illusions, but temporary yet effective quantum events. In conclusion, although virtual particles are not concrete, like classical particles, they directly contribute to the functioning of the physical universe. They are the living proof of the quantum vacuum. Their existence may be shadow-like, but the shadow itself is also a reality. This forces us to rethink the concepts of existence and non-existence. In physics, anything that is invisible but influential cannot be ignored. Virtual particles are at the forefront of these invisible architects. 10. No particle can be completely at rest. There's a fundamental rule in quantum mechanics. You cannot know the position and momentum of a particle with absolute certainty at the same time. This is Heisenberg's uncertainty principle. This principle is so profound that it states that no particle in the universe can be in a state of absolute rest. Because if a particle were completely motionless, its momentum would be zero. In that case, its position would have to reach infinite uncertainty, which is physically impossible. Therefore, at every point in the universe, every particle is in some form of vibration, some form of motion, even at the lowest energy level. This means that even empty space can never truly be still. This situation is not limited to the microscopic world. The entire universe is built upon these quantum vibrations. The constant motion of subatomic particles forms the building blocks of time and energy. Stillness may be an abstraction, but it can never truly exist in nature. This shows us that all structures in the universe are fundamentally based on a state of motion. Even empty space is filled with the vibrations of an infinite number of quantum fields. This principle also guides technology. For example, precise systems such as lasers, atomic clocks, and quantum computers rely on the predictability of these particle movements. If particles could come to a complete stop, many processes, such as measuring time, would break down. The flow of energy in the universe continues through this constant motion, enabling physical laws to function. So, stillness is just a conceptual ideal. It's not real. This understanding changes how we perceive matter and even time. In a universe where everything is constantly moving, the concepts of still and fixed become relative. Every particle, every field, every direction vibrates at the quantum level. These vibrations are the breath of the universe. Stillness is only a mental refuge, but nature is always in motion. And the interesting thing is that this motion arises from the void. 11. Energy cannot be created from nothing, but how does the void overcome this? According to classical physics, energy is conserved. It cannot be created from nothing, nor can it be destroyed. This law forms the basis of all physical processes in the universe. However, the quantum world opens a very unusual window that bends this absolute rule. For short periods of time, energy can be borrowed. Since Heisenberg's uncertainty principle also predicts uncertainty between energy and time, the creation of energy for a short time is theoretically possible. In this process, virtual particles emerge from the quantum vacuum, exist for a very short time, and then disappear again. Thus, energy is technically not created from nothing, but derived from the potential of the vibrating vacuum. This occurs without violating the classical law of energy conservation, because these energy fluctuations are extremely short-lived. This process occurs through vacuum fluctuations or zero-point energy events. Within a specific time interval, small deviations in the system's energy may occur, leading to the creation of virtual particles. These events are so fast and small in scale that they cannot be measured by classical physics. However, their effects are significant. These quantum fluctuations may have even led to the formation of building blocks in the early moments of the universe. Therefore, even though energy appears to emerge from nothing in an instant, these events actually occur within the framework permitted by nature. From a cosmological perspective, the universe itself may have emerged from such an energy fluctuation. If the quantum vacuum remains unstable for a sufficiently long period, this could lead to the emergence of real particles and even a universe. This view suggests that the universe came into existence through a kind of quantum tunneling event. Thus, energy does not emerge directly from nothing, but rather from a point filled with potential. This is a creation process that overturns classical understandings, but is logical from the perspective of quantum physics. This shows us that the deepest realities of the universe sometimes operate through processes that appear paradoxical. Energy conservation still holds true on large scales. However, on small scales, the rules of nature are much more flexible. Emptiness is the stage for this flexibility, and there, creation and destruction are both possible at any moment. In this sense, quantum emptiness is both the mystery and the engine of the universe. 12. Is nothingness absolute non-existence, or is it potential itself? When the human mind thinks of nothingness, it usually imagines an absolute void, the complete absence of all existence. However, the reality revealed by modern physics renders this intuitive understanding almost completely invalid. Because at the quantum level, nothingness, where nothing exists, is almost impossible. Even in the spaces we perceive as empty, quantum fields constantly vibrate, virtual particles come and go, and energy fluctuations occur. In this case, nothingness is actually the source of possibilities that have not yet been realized, the very essence of potential. In other words, there is nothing in the universe in the true sense of the word. There are only possibilities that have not yet become things. This understanding is also quite striking philosophically, because in traditional metaphysics, nothingness is, by definition, the absence of everything. But quantum physics shows us that this kind of absolute nothingness is only a theoretical abstraction. In the physical universe, energy fields always contain some amount of motion, and this motion has the potential to create even the most basic building blocks. This suggests that nothingness may actually be a kind of first state of everything. Perhaps nothingness was the fullest state before the universe, because it contained infinite possibilities. The conclusion drawn from this is profound. Nothingness is not merely an absence, but also the boundary of existence. Concepts such as quantum tunneling, vacuum fluctuations, and zero-point energy show us how this boundary can bend, and sometimes even be crossed. Thus, even what we call nothingness in the physical universe may actually be a threshold of events. The birth of the universe may have occurred precisely at this threshold. From a state of nothingness, an exploding potential may have emerged, giving rise to time, space, and matter. These ideas prompt us to re-examine the existence of the universe in both a scientific and metaphysical context. If nothingness is actually a ground full of potential, then the universe was not born out of emptiness, but out of infinite possibility. This shows us that even in a place that appears to be nothing, the seeds of creation may have been sown. In this sense, quantum vacuum is not nothingness, but creative potential itself. 13. How does energy emerging from emptiness turn into real particles? In quantum field theory, vacuum energy, and virtual particles are generally considered temporary and unobservable phenomena. However, under certain special conditions, these temporary phenomena can become permanent and observable. This occurs when the vacuum loses its stability in a region of high energy density. In the quantum vacuum, virtual particle pairs are constantly being created and annihilated. However, if there is enough energy or a strong enough field in the environment, such as near a black hole or under a strong electromagnetic field, one of the virtual particle pairs can transform into a real particle and remain in the vacuum. The other is annihilated along with its negative energy. This process is particle creation itself. One of the most iconic examples of this phenomenon is Hawking radiation. At the event horizon of black holes, quantum fluctuations result in the formation of a virtual particle pair. One of these pairs falls into the black hole, while the other escapes and becomes a real particle. As a result, the black hole loses energy. In other words, a temporary particle that appears in empty space can become a permanent entity in the universe under the right conditions. This event is a fundamental quantum process that transcends the limits of classical physics and demonstrates how new particles, and therefore new energies, can emerge in the universe. Similarly, in experiments conducted under very strong electromagnetic fields, the production of real particles from empty space can be observed. In such experiments, photons can cause virtual particle pairs to separate and transform into real particles by forcing the structure of the vacuum. This demonstrates that empty space is essentially a stage ready to produce particles. When sufficient energy or instability is provided, space behaves like a birth room and produces matter from within itself. The existence of these processes proves that space is a much more active environment than we had imagined. Space is not merely a void. Rather, it is the direct source of potential energy and particle production. Therefore, an external intervention may not always be necessary for new things to emerge in the universe. The void itself can create new particles under the right conditions. This reveals that the laws of physics encompass not only order, but also creation. 14. Did the universe emerge from a quantum void? One of the most exciting and profound questions in cosmology is, where did the universe come from? While the answer was once sought through religious or philosophical approaches, today science, particularly the combination of quantum theory and general relativity, offers a much more concrete approach to this question. According to quantum cosmology, the universe may have emerged from a completely unstable quantum vacuum. This vacuum was not ordinary nothingness. It was a structure filled with energy, fluctuating and charged with potential. Through a quantum tunneling process within this structure, an expansion from zero volume, the cosmic birth, occurred. The event we call the Big Bang may have been the result of this quantum instability. This idea is supported by theoretical physicists such as Stephen Hawking and James Hartley with their no-boundary hypothesis. According to this model, time has no beginning. The moment of origin lies outside the classical definition of space-time. The universe emerged from the quantum void, much like a wave rising from the surface of water. In other words, the beginning of the universe was more of a transition process than a single moment, a transition from a timeless void to a temporal structure. This goes beyond the classic narrative of nothing existed, then there was an explosion, because in this model, that nothing is already filled with potential. The classical interpretation of the Big Bang relies on a singularity of infinite density and temperature. However, such singularities are points where the laws of physics do not apply, making them more confusing than explanatory. Quantum cosmology aims to overcome this problem by explaining the origin of the universe within the framework of natural laws. According to this model, the universe originated from a small quantum-level vibration, began to expand rapidly, and this expansion continues to this day. This expansion is even connected to the nature of space itself, as vacuum energy continues to push the universe outward. This understanding makes the existence of the universe even more fascinating, because existence did not arise from nothingness, but from a quantum process full of potential. This process is based on the principle of spontaneity. When nature passes from its lowest state of energy to a lower state, existence can emerge. The universe itself is the result of such a transition. This means that the universe itself may have emerged from the realization of a quantum possibility. 15. What is zero-point energy, and why does it never drop to zero? In quantum physics, the concept of zero-point energy demonstrates that absolute stillness is impossible even in a vacuum. This completely overturns the classical physics understanding that if energy is zero, the system is at rest. At the quantum level, a particle or field cannot come to a complete stop, even if it reaches absolute zero temperature. According to Heisenberg's uncertainty principle, the position and momentum of a particle cannot be known with absolute certainty at the same time. This means that a particle cannot be in a state of complete rest, because then both its position and momentum would be known. This fundamental uncertainty creates a minimum energy level that is always present in everything in the universe. This is called zero-point energy. This energy is not just a theoretical curiosity. It is a very real and measurable phenomenon. In an experiment known as the Casimir effect, when two metal plates are brought close to each other in a vacuum, the plates are attracted to each other due to the pressure of zero-point energy in the space between them. This clearly demonstrates that emptiness is not nothing. Even in a vacuum, there is energy, and this energy can create physical effects. Zero-point energy is not only microscopic, but can also be effective on a cosmic scale. Some theoretical connections have been drawn between zero-point energy and dark energy, which is believed to accelerate the expansion of the universe. So why can't this energy be reduced to zero? Because at the quantum level, nature does not accept a completely stationary system. Every particle, every field, exists with a certain amount of vibration and uncertainty. These vibrations cannot be completely eliminated, no matter how much they are cooled. So even the most silent state in the universe actually has a hum. This hum is the absolute foundation of existence. Zero-point energy is the silent sea of energy hidden behind everything, and that is precisely why it can never be reduced to zero. This completely changes our view of the universe and existence, because even emptiness is energy, even stillness is dynamic. Zero-point energy is a fundamental force that vibrates within every substance and field. The structure of the universe depends on this energy, and everything that exists may have originated from it. This idea suggests that even emptiness can be creative. At the very core of existence, there is always a flicker of movement. 16. How do quantum fluctuations influence the fate of the universe? Quantum fluctuations are the smallest vibrations of quantum fields, and although they cannot be directly observed, their effects are significant, especially in the early stages of the universe, immediately after the Big Bang. These fluctuations shaped the large-scale structure of the cosmos during the inflation, rapid expansion process. Quantum fluctuations create very small energy differences in different regions of the vacuum. These differences cause microscopic fluctuations to transform into macroscopic structures during expansion. The energy imbalances that laid the groundwork for the formation of galaxies, stars, and ultimately planets originated from those initial quantum vibrations. This means that the current large-scale structure of the universe actually originated from uncertainty and quantum chaos. The smallest wave created huge structures over time. Even at a moment when there was no order, these micro-vibrations at the quantum level laid the foundation for future order. The cosmic background radiation, which we call the baby picture of the universe, carries traces of these fluctuations. The temperature irregularities in this photograph are the frozen traces of these first quantum oscillations. In other words, a wave in space could have turned into a galaxy billions of years later. This understanding leads us to question the concepts of destiny and chance at a scientific level. If the current state of the universe is nothing more than the growth of random quantum fluctuations, this redefines both determinism and free will. Perhaps the nature of the universe is nothing more than waves randomly emerging from a sea of potential and eventually forming order over time. This order is not the result of an absolute plan, but of the spontaneity of quantum nature. Ultimately, quantum fluctuations are fundamental processes that determine the fate of the entire cosmic structure, not just at the microscopic level. These energy waves vibrating in space have evolved into matter, structure, and order, forming the architecture of the universe. In a sense, the fate of the universe is written by invisible vibrations swirling in the void. 17. Why are quantum fields present at every point in space? According to quantum field theory, every fundamental particle in the universe is actually a quantum of a field. For example, an electron is a vibration of the electron field, while a photon is an excitation of the electromagnetic field. These fields are present at every point in space and constantly fluctuate. Therefore, an electron does not exist only in a specific place. Its field encompasses the entire universe. Thus, quantum fields are woven into the fabric of the universe. Every cubic centimeter of space is an energy field in which these fields vibrate. In other words, there is no such thing as empty space in the universe. This idea completely transforms the concept of emptiness. Emptiness is no longer just a field devoid of matter, but rather a structure in which constantly vibrating energy networks are intertwined. Each quantum field interacts with others, and these interactions form the basis of new particles, forces, and events. A quantum field vibration in space can cause a particle to emerge, while a field fluctuation can give rise to a force. Therefore, at every moment and at every point, there is a potential for creation. Thanks to this structure, universal constants, physical laws, and particle behavior are the same everywhere in the universe, because all these rules are based on the existence of quantum fields. In other words, the laws of nature are not specific to a particular region of space. They are valid throughout the entire universe, thanks to the universal spread of quantum fields. The form in which these fields are embedded in space is like an invisible software that constitutes the codes of the universe. Everything is read from this software, and every entity is loaded from these fields. In conclusion, quantum fields are not merely carriers of particles. They are the very foundation of existence. Without them, space would be nothing more than geometry. But thanks to them, space becomes a living, vibrating fabric of energy. Understanding quantum fields is equivalent to understanding the universe itself, because the source of everything is these invisible yet omnipresent fields. 18. Why might the universe have emerged from quantum space? One of the deepest questions about the beginning of the universe is, how did everything begin? At this point, the classic Big Bang model says that the universe began expanding from a point in a dense and hot state. But this model cannot provide a clear explanation of what came before that first moment, or what triggered it. This is where the concept of quantum vacuum comes into play. Quantum field theory shows that what we call vacuum is not actually empty, but a structure filled with constant energy fluctuations. These fluctuations occasionally create and annihilate short-lived particle pairs. In this quantum foam environment, larger structures may emerge statistically rarely. According to some theories, such a quantum vacuum could have undergone a sudden jump in energy density, leading to the Big Bang that initiated our universe. In other words, the universe may not have emerged from nothing, but rather from a quantum vacuum with energetic potential through a spontaneous phase transition. In this case, the beginning of the universe is not a created event in the classical sense. It is more of a spontaneous transition within the possibilities of quantum nature. The void is not merely nothingness, but the source of potential. This idea provides a powerful answer to the paradox of creating something from nothing within the framework of quantum physics. This theory gives rise to the idea that other universes may have been born within the same quantum foam. In other words, our universe may be just one example of a vast cosmic multiverse, a multiverse structure. All of them may exist with their own constants, their own laws, and perhaps their own time. What they all have in common is that they were born from the same quantum void. In this case, our universe is not unique, but merely the result of a random fluctuation. This view has a revolutionary impact on both the origin of the universe and our idea of cosmic loneliness. In this sense, the quantum vacuum becomes a concept that is not only physical, but also philosophical. Because the universe itself has emerged from what appears to be nothingness, but is actually a nothingness full of potential. This nothingness is, in fact, a starting point that carries infinite possibilities. Existence is therefore not an absolute thing. It is a constant fluctuation that creates itself. 19. How does vacuum energy affect the expansion of the universe? The most observable behavior of the universe is its expansion. However, observations made at the end of the 20th century revealed that this expansion is not slowing down, but rather accelerating. This surprising discovery could not be explained within the framework of classical physics. This is because the matter and energy present in the universe should slow down the expansion. This is where the concept of vacuum energy, or more popularly, dark energy, comes into play. The zero-point energy present in the vacuum may carry enormous energy potential even in the seemingly empty spaces of the universe. This energy directly affects the geometry and destiny of the universe. Quantum fields exist at every point in space, and their zero-point vibrations are embedded in the fabric of space. The total energy of these vibrations is expressed by a term called the cosmological constant. This cosmological constant, which once appeared as a mathematical correction in Einstein's theories, has now become the fundamental factor explaining the accelerating expansion of the universe. Vacuum energy produces a pressure that causes space itself to expand. This pressure acts as a repulsive force, unlike gravity. Thus, vacuum energy acts as a cosmic fuel, accelerating the expansion of the universe. However, an intriguing paradox arises here. According to quantum field theory, the magnitude of vacuum energy is approximately 10 to the power of 120 times greater than the value derived from cosmological observations. This is one of the greatest problems in modern physics, the cosmological constant problem. Why does vacuum energy appear to be so large, yet the universe is expanding so slowly? This question remains unanswered. Perhaps there is a balancing mechanism at play that we have yet to fully understand. Nevertheless, the existence of vacuum energy has been one of the most critical factors shaping the evolution of the universe. This invisible energy may be shaping a scenario that will lead to galaxies moving apart, cosmic voids expanding, and ultimately the heat death of the universe. In short, this invisible energy within the void is determining the visible fate of the universe. 20. Why do quantum fields affect everything, even though they cannot be seen? Quantum fields cannot be observed because they are not matter or energy in the classical sense, but rather mathematical and physical structures spread throughout space. However, this does not mean they are ineffective or insignificant. On the contrary, quantum fields are fundamental entities that are not directly visible, but whose effects are felt throughout the entire universe. All particles emerge as a result of the fluctuations of these fields. In other words, an electron exists because the electron field has been excited at a particular point. The same applies to photons, quarks, neutrinos, and all other particles. Therefore, quantum fields form the invisible yet decisive infrastructure of the universe. Without these fields, the laws of nature would not exist either. This is because the transfer of forces between particles, such as electromagnetic interactions, occurs through these fields. If an electron and a proton attract each other, this happens through the exchange of photons via the electromagnetic field. In other words, if there is an effect visible in empty space, it is actually the vibration of an invisible field. Therefore, quantum fields are the driving force behind every physical event, even though they cannot be directly observed. Without them, matter cannot exist, forces cannot function, and even time and space would have no meaning. The influence of quantum fields is so widespread that we experience their effects in our daily lives without even noticing them. For example, light from the sun is formed by the excitation of the electromagnetic field as photons. The structure of atoms is determined by the interaction between the electron field and the nucleus. These interactions give rise to chemistry and shape life. At the core of all this are invisible but ever-present fields. In other words, we are constantly interacting with these fields, but we cannot perceive them directly. It is like the wind, which cannot be seen but whose effects can be felt. Quantum fields are at the center of modern physics and represent the deepest layer of reality. Without them, the universe would be empty. But thanks to their existence, even emptiness is filled with energy, and these invisible entities, like invisible hands that determine everything, silently govern the workings of the universe. Not being able to see them does not mean they do not exist. It only shows the limits of our perceptions. 21. Is space really empty, or is it a sea of energy? The concept of space has evolved many times throughout history. In ancient times, space was considered to be complete nothingness. It was thought that nothing existed where there was no matter. However, modern physics has almost completely reversed this idea. Today, space, as we understand it, is actually an extremely dynamic environment filled with energy. This vacuum is not completely stationary, even when brought to absolute zero temperature, due to quantum fluctuations within it. Quantum field theory describes this emptiness as an ever-vibrating ocean of energy that constantly creates and destroys particles. Thus, space may be one of the most active regions in the universe. In this quantum vacuum, particle-antiparticle pairs called virtual particles constantly appear and disappear. This process is a result of Heisenberg's uncertainty principle. There is uncertainty between energy and time, and this uncertainty allows energy to be borrowed for a short time. As a result, the place where nothing exists actually becomes a stage where an infinite number of potential events occur. Therefore, the void is not the absence of physical existence, but the presence of constant potential. Perhaps everything in the universe is simply different states or temporary organizations of this energetic background. Furthermore, the energy of this void has been experimentally observed. The Casimir effect is the attractive force between two metal plates and is caused solely by vacuum fluctuations. This phenomenon is one of the most striking examples, physically proving that emptiness contains energy. Additionally, this empty space energy may be connected to dark energy, which is thought to accelerate the expansion of the universe. Thus, this invisible energy could be determining the fate of the entire cosmos. In conclusion, the word vacuum no longer represents the calmest aspect of reality, but rather its most dynamic one. The vacuum is not a static void. It is an ocean of energy embedded in the fabric of time and space. This understanding redefines physical existence. Matter, energy, and even time are temporary actors on this invisible stage of energy. 22. How do virtual particles emerge, and what are they for? Virtual particles are not like particles in the classical sense. They are unobservable entities that emerge during the fluctuations of quantum fields, yet their effects can be felt. Virtual particles can appear in a particle-antiparticle pair in the void, and then annihilate each other, reverting back to energy. These events typically occur in extremely short time intervals and are therefore not directly observable. However, the effects of these particles produce measurable physical results. For example, experimental phenomena such as the Casimir effect or the Lamb shift indirectly demonstrate the existence of virtual particles. These particles play a crucial role in quantum electrodynamics, QED. The formation of the electromagnetic force between two charges is explained by the exchange of virtual photons. Similarly, the strong nuclear force and the weak nuclear force are also transmitted through virtual particles. Thus, many of the fundamental forces in nature cannot function without these transient entities. They act as invisible messengers in the infrastructure of reality. Although they can never be physically detected, Their movement ensures the balance of forces in the universe. However, virtual particles not only play a role in the transmission of physical forces, but also open a window into the nature of the universe. Because the emergence of virtual particles is a result of the energetic structure of the vacuum. These particles are a direct product of the uncertainty between energy and time. This shows us that time and energy do not exist in absolute certainty, but move within a probability plane. Reality is not rigid and definite. It is dynamic and filled with possibilities. Virtual particles are invisible, yet decisive entities. Through them, forces are transmitted, fields interact, and the universe is held together. These particles are like the invisible backbone of the quantum world. Although they are short-lived and cannot be directly observed, reality exists through their effects. 23. How did the Casimir effect prove that empty space carries energy? The Casimir effect is an extraordinary physical phenomenon predicted by physicist Hendrik Casimir in 1948, which experimentally confirmed that the quantum vacuum carries energy. This effect is one of the most compelling pieces of evidence showing that empty space is not truly empty, but rather constantly filled with energy fluctuations. In the Casimir experiment, two conductive plates are placed very close to each other, and it is assumed that there is no matter or energy in the space between them. However, this is not the case. According to quantum field theory, an environment forms between the plates where only waves of certain frequencies can fit. As a result, a difference arises between the energy of the surrounding space and the vacuum energy inside. This energy difference causes the two plates to be attracted toward each other. This force is known as the Casimir effect. The most surprising thing here is that this force cannot be explained by any classical force. In other words, this attraction is neither electromagnetic nor gravitational. It is a purely quantum-based effect, arising from vacuum fluctuations. This experiment is revolutionary because it experimentally demonstrates that empty space is actually filled with energy. Before this, empty space was considered a completely passive, inactive environment. The Casimir effect is a manifestation of the direct interaction of quantum fields with the physical world. This has led theoretical physicists to take vacuum energy seriously. This energy is not merely a theoretical abstraction. It is an experimentally measurable reality. This has fundamentally altered our understanding of the fundamental structure of the universe. Once it became clear that even empty space has physical effects, it began to be viewed as an active component of the universe. Today, the Casimir effect has found applications not only in fundamental physics, but also in fields such as nanotechnology. In other words, this quantum phenomenon helps us understand the largest structures in the universe and produce the smallest machines. Emptiness once again emerges as an invisible yet powerful force. 24. How can the energy of nothingness turn into matter? Although nothingness is perceived as a state of absence in classical understanding, this definition becomes invalid in quantum physics. What we call quantum vacuum is actually filled with zero-point energy. In other words, even nothingness carries an energetic foundation. In this foundation, virtual particles emerge and disappear. This dynamic is made possible by Heisenberg's uncertainty principle, which allows energy to be borrowed for short periods. It is precisely this energy density that can transform into matter under certain conditions. This process is directly linked to Einstein's famous formula E equals mc squared. When energy becomes sufficiently concentrated, it can transform into mass, that is, matter. Therefore, with enough energy, physical entities can be produced from what is referred to as nothingness. This idea is not merely theoretical. It is also supported by experimental evidence. In particle accelerators, the collision of high-energy photons has resulted in the production of particle-antiparticle pairs. These experiments demonstrate that matter can be produced directly when energy density is sufficient. In such productions, there is no concrete matter at the outset. Only energy is emitted within the electromagnetic field. When this energy crosses a critical threshold value, it manifests as quarks, leptons, and other fundamental particles. In other words, energy can transform into the building blocks of the physical universe. A similar process is also present in the Big Bang model. In the first moments of the universe, matter and antimatter were continuously produced and annihilated within an environment of immense energy density. However, a very small excess of matter in this process formed the building blocks of the present-day universe. Therefore, the first matter was born from pure energy, perhaps from an environment that appeared to be absolute nothingness. This process makes the creation of the universe not just a religious or philosophical event, but a physical possibility. This knowledge reshapes both the big questions about the origin of the universe and our visions of future technologies. If matter can be created from the energy of nothingness, humanity may one day be able to engineer these processes. Energy from nothingness, matter from energy. This cycle is one of the deepest mechanisms underlying the creation of the universe. 25. Why is there something rather than nothing in the universe? This question is perhaps the most fundamental question of the philosophy of existence and cosmology. Why is there something rather than nothing? Apparently, the universe is not the natural state of nothingness. Quantum physics offers a different perspective on this question. The energy constantly fluctuating in quantum space can occasionally form permanent structures through symmetry breaks. These structures can be particles, fields, or even space-time itself. In other words, quantum nature is not absolute stillness. It is a dynamic and statistically moving stage. Within this movement, the emergence of existence may be inevitable. Existence is the unstable state of non-existence. Physicists explain this situation through quantum instability. A state of absolute symmetry in the quantum vacuum is unstable. Just as it is impossible for a pencil to balance on its tip, the quantum vacuum tends to create something with a small imbalance. This creation can take the form of particles or result in the birth of an entire universe. This perspective suggests that the existence of the universe is not exceptional, but a statistically natural outcome. Perhaps nothing is not stable, and that is why something exists. This topic resonates not only in physics, but also on a philosophical level. Can nothingness exist in an absolute sense? Or does every notion of nothingness contain some form of potential? Quantum physics suggests that even nothingness could be a building block. Thus, the line between existence and nothingness becomes blurred. Existence may not be merely a state of being, but rather an intermittent expression of potential. Ultimately, this question may need to be approached in reverse. Perhaps existence is the norm. If there is no mechanism preventing existence from emerging, then why shouldn't the universe exist? This idea removes the formation of the universe from the realm of mystical miracle and makes its existence an inevitable outcome. So perhaps the existence of something is a more natural state than the non-existence of anything. By the way, if you like my video and subscribe, that's the most effective way to support me. 26. How is dark energy connected to the void? Dark energy is defined as a mysterious force that accelerates the expansion of the universe. But where does this force come from? This is where the concept of quantum vacuum comes back into play. Physicists have begun to link the source of dark energy to vacuum energy. This is because quantum fields are spread throughout every point in space, and the zero-point energy of these fields is present even in a vacuum. This energy cannot be observed in the classical sense, but its effects are felt on a cosmic scale. In particular, it is thought that the repulsive force causing galaxies to move away from each other at high speeds originates from this energetic structure of the vacuum. Vacuum energy is evenly distributed throughout all of space. This aligns perfectly with the properties of dark energy: homogeneous, non-diluting, and constant over time. For this reason, many cosmologists argue that dark energy is actually an inherent property of the vacuum itself. This energy causes space to become more effective as it expands, because vacuum energy reappears in every new unit of space. This causes the universe to expand at an increasingly rapid rate. It is as if space is a self-expanding energy source. However, there are serious problems with this theory. The amount of vacuum energy calculated by quantum field theory does not match observations. In theory, the magnitude of vacuum energy is 10 to the 120th power times greater, which is one of the greatest discrepancies in science. This discrepancy remains one of the greatest puzzles for modern physics to solve. Perhaps a physical law we have not yet discovered balances this energy with the observed rate of expansion. The relationship between dark energy and space is central not only to cosmology, but to all of physics. Space is no longer just a backdrop. It is an invisible player determining the fate of the universe, and the true nature of this player remains largely unknown. However, one thing is certain: the hidden energy within space is shaping the future of the universe. 27. Did the universe really originate from nothing? This question about the origin of the universe is one of the most fundamental questions in both science and philosophy. The Big Bang Theory, currently the most widely accepted cosmological model, proposes that the universe originated from an extremely dense and hot point and expanded to its present state. However, physics still cannot provide a clear answer about the before or source of this starting point. According to some theories, this starting point did not actually originate from nothingness in the true sense of the word, but rather from an energetic and potential-filled quantum vacuum. This vacuum is not a void in the classical sense. It is a structure where quantum fields constantly vibrate and virtual particles are born and disappear. In other words, the place where the universe was born may not be a void as we imagine, but a dynamic and energetic structure. Quantum cosmology offers some very interesting ideas on this subject. For example, some quantum gravity models suggest that the universe emerged from the vacuum through quantum tunneling. According to this model, the universe transitioned into existence from a state where time and space did not exist, essentially from nothing, by tunneling through the vacuum. Such a transition cannot be explained by classical physics. It can only be understood through quantum physics. Therefore, although the birth of the universe from nothing may sound like science fiction, it is a phenomenon that is seriously considered in modern physics theories. Furthermore, this type of birth does not necessarily imply a singularity. In some theories, there does not need to be a singularity, i.e., infinite density and temperature at the beginning of the universe. Instead, due to the quantum properties of space-time geometry, there may have been a soft start. This suggests that what we call the beginning may actually be a process in which classical time does not apply. In other words, perhaps the universe has no beginning. There is only a transition point where we reach the limits of our perception of time. In conclusion, the idea that the universe emerged from nothing seems both impossible and inevitable, according to current scientific thinking. Everything already exists in potential within what we call nothingness: particles, energy, fields. The emergence of the entire universe from that invisible structure is becoming an increasingly plausible and powerful hypothesis in science. So the birth of the universe was not an explosion, but perhaps a silent quantum vibration. 28. How can a universe arise from quantum fluctuations? Quantum fluctuations are energy changes that are not stationary, even at the smallest scale of space-time, but are in constant motion. These fluctuations occur even in a vacuum at absolute zero temperature. In other words, even when the universe is in a state of nothingness, these energy vibrations continue. According to quantum field theory, when these fluctuations reach a sufficient size, they can create their own gravitational field and form a pocket universe. This idea becomes even more interesting when combined with the inflation theory. According to inflation theory, such a tiny energy region formed after quantum fluctuations can rapidly expand and become a universe on its own. This type of formation process challenges classical notions of causality. This is because it involves the creation of time and space from a structure that is timeless and spaceless. However, the concept of quantum tunneling makes this transition possible. In quantum physics, a particle can pass through an obstacle using the tunneling effect, even if there is an obstacle in its path. Similarly, an entity can emerge from nothingness through tunneling. This concept suggests that the universe itself may have emerged through a quantum tunneling process. In other words, the universe could be the random result of a quantum fluctuation. However, this randomness has transformed into a reality that generates its own laws. Furthermore, this process makes it possible for not just one universe, but perhaps many universes to emerge. The limitless nature of quantum fluctuations suggests that multiple universes, multiverse, with different physical laws could exist. In other words, our universe could be just a bubble in the quantum sea. Independent universes, each with its own time, space, and physical constants, could exist within this quantum foam. This idea is also used to explain why the universe has the conditions suitable for life. We exist because we are in a universe that makes life possible. The idea of a universe emerging from quantum fluctuations reveals how delicate the balance of reality is. Perhaps a small energy fluctuation created the beginning of all time, space, and existence. In other words, the origin of the universe may have come from a microscopic vibration rather than a massive event. This is a cosmogonically modest yet profoundly revolutionary perspective. 29. Is space actually an energetic medium? At first glance, space may seem like a completely static and neutral field where nothing exists. However, modern physics, particularly quantum field theory, has completely overturned this understanding. According to quantum theory, space is not nothing as previously believed. On the contrary, space is an energetic and dynamic structure where various quantum fields constantly fluctuate and virtual particles are constantly being created and annihilated. These fluctuations are not random. They occur continuously in accordance with Heisenberg's uncertainty principle. Therefore, space is filled with energy. This energy is called a vacuum energy or zero-point energy. In other words, there is vibration and energy in every corner of space, even in absolute emptiness, even in the void. This energetic structure gives rise to some surprising results. For example, the Casimir effect is an experimental proof of the energetic nature of space. When two conductive plates are brought very close together, the quantum fluctuations between them change relative to the surrounding environment, resulting in an observable attractive force between the plates. This demonstrates that physical effects can arise even in empty space. In short, space is not passive, but an active player. This energy, which we cannot see but whose effects we can feel physically, plays a major role in the fundamental workings of the universe. Furthermore, quantum fields encompass not only matter, but also fields themselves. In addition to particles such as electrons and quarks, quantum fields such as the electromagnetic field and the Higgs field are also active in space at all times. The existence of these fields gives mass to the fundamental particles of the universe, determines the interactions of force-carrying bosons, and shapes the way natural laws operate. All of this shows that space is not ordinary, but a complex network that determines the nature of the universe. In other words, space is not a cosmic zero point, but a vibrating fabric that forms the infrastructure of the universe. Therefore, space is no longer a symbol of nothingness, but of potential and constructive energy. This invisible energy in the void of space influences everything from the movement of stars to the distribution of galaxies. Understanding the energetic nature of space is one of the first steps toward unraveling the deep structure of the universe. 30. Why does something emerge where there is nothing? This question can be both intuitively and scientifically perplexing. If there is nothing, how can something come into existence? However, quantum physics provides an unconventional, yet robust answer to this question. Nothingness is not a static state in the classical physical sense. According to quantum field theory, even the environment we call nothing is filled with quantum fluctuations. These fluctuations can create random energy densities, and these energy densities can, under certain conditions, transform into particles, fields, or even an entire universe. Therefore, there is no need for an absolute beginning for something to form. Quantum instability is sufficient. The uncertainty principle emerges as the fundamental principle that makes this process possible. According to this principle, we cannot establish absolute certainty between energy and time. For a short period of time, the energy of the system can be borrowed, and during this time, virtual particles can appear. These virtual particles usually disappear immediately, but under certain special conditions, this temporary state can become permanent. The birth of something stems from this instability. In other words, the existence of the universe is not an exception, but a natural consequence, of quantum laws. We can observe something similar in nature. In radioactive decay, the atomic nucleus is in a state of equilibrium, but this equilibrium is constantly tested at the quantum level. And when there is sufficient quantum fluctuation, the system becomes unstable and decay occurs. This situation shows that a system, even if it appears stationary, is actually in a state of constant change and potential. What we call nothingness may also be such a quantum equilibrium. On the surface, it appears as if there is nothing, but it contains potential energy. Therefore, instead of searching for reasons why something comes into existence, it may be more meaningful to ask, if there is nothing to prevent something from coming into existence, why shouldn't it? At the quantum level, such formations are statistically inevitable. Even emptiness is creative because it contains instability. This instability is the spark of existence. 31. Can the energy in space really be measured? The energy in space, or vacuum energy, cannot be observed directly, but it can be measured indirectly, and these measurements strongly confirm its reality. One of the most well-known examples is the Casimir effect. In this experiment, two conductive plates placed very close to each other attract each other when they are in a vacuum. This attractive force arises from quantum fluctuations in the space between the plates, which disperse differently compared to the surrounding vacuum. In other words, even in a vacuum, energy exists and produces physical effects. This is experimental proof that the vacuum is not nothingness, but an active energy field. Additionally, quantum electrodynamics, QED corrections, also account for the effects of vacuum energy. The energy levels of fundamental particles like electrons are influenced by the vacuum fluctuations around them. Such interactions can be measured experimentally with high precision and agree exactly with theoretical calculations. For example, phenomena like the Lamb shift directly demonstrate the vacuum's effect on particles. This proves that there are measurable physical effects in the vacuum. Thus, the vacuum is not an unmeasurable abstraction, but an observable structure capable of producing physical effects. At a more macroscopic scale, the relationship between dark energy and vacuum energy is understood through measurements of the universe's expansion rate. The accelerating expansion of the universe directly points to the existence of vacuum energy. This energy, known as the cosmological constant, has been modeled by adding a term to Einstein's equations. Today, supernova observations and analyses of cosmic microwave background radiation have reached a level where they can measure the magnitude of this energy. This clearly demonstrates that space carries measurable energy. In short, the energy in space is not an abstract idea. It is a real phenomenon with measurable effects that can even be detected using technology. While it may not be possible to see it directly, we can observe its traces clearly on both microscopic and cosmic scales. This energy plays a decisive role in both the microscopic nature of the universe and its large-scale destiny. 32. Is dark energy related to the structure of space? Dark energy is defined as a mysterious force that causes the universe to expand at an accelerating rate. This phenomenon was first discovered in 1998 through the observation of distant supernova. While scientists expected the expansion of the universe to slow down, they instead observed that the expansion rate was increasing. This unexpected situation led scientists to believe that an unknown form of energy had become dominant in the universe. This energy is called dark energy. Interestingly, dark energy appears to be evenly distributed throughout the universe and does not seem to decrease in density over time. These properties make it directly connected to the fabric of space itself. Quantum field theory, on the other hand, suggests that space is actually filled with zero-point energy, meaning that space is never truly empty. This energy stems from quantum fluctuations that exist at every point, at every moment. Theoretically, this energy is linked to the cosmological constant, although Einstein later called the cosmological constant he added to his equations to keep the universe static, the biggest mistake of his life. Today it is thought that this constant could be used to explain the accelerating expansion of the universe. This suggests that dark energy may originate from energy that already exists in the nature of space. However, this raises a major problem. When quantum field theory calculates the magnitude of vacuum energy, it finds a value trillions of times greater than the observed dark energy density. This is known as the cosmological constant problem, one of the greatest mysteries in the history of physics. So we still don't know for sure whether vacuum energy is really dark energy. If dark energy is indeed an inherent property of the structure of space, this would indicate that the laws of nature operate at a much deeper, perhaps as yet undiscovered, level. Therefore, dark energy may be directly linked to the structure of space, but the nature of this connection remains a great mystery. Perhaps space has a much more complex structure than we imagine. A structure that expands on its own, determines the fate of the universe, and behaves like an unconscious but universal force. Solving this mystery would not only mean understanding dark energy, but also unraveling the nature of space itself. 33. Can vacuum energy influence the fate of the universe? Vacuum energy is a form of energy arising from zero-point fluctuations within space. This energy plays an extremely significant role on a cosmological scale. Because vacuum energy exists uniformly throughout space, it can exert a dominant influence on the overall dynamics of the universe. If vacuum energy is truly constant, that is, if it does not change over time, then the universe will continue to expand at an accelerating rate forever. This is a critically important scenario for the fate of the universe. This type of expansion would separate galaxies, halt star formation, and eventually leave the universe cold, dark, and empty. This scenario is known as the Big Freeze. However, if vacuum energy is not constant, but instead increases or decreases over time, things could take a much more dramatic turn. For example, in some models, if vacuum energy increases over time, the universe begins to expand so rapidly that even atoms are torn apart. This is called the Big Rip. In this case, vacuum energy not only directs the expansion of space, but also breaks down the structure of matter. On the other hand, if vacuum energy somehow becomes negative, the expansion of the universe could stop and then reverse. This gives rise to the Big Crunch scenario. In other words, vacuum energy could be a cosmic element that determines not only the birth, but also the end of the universe. Current cosmological observations suggest that vacuum energy is positive and constant, meaning that the universe will continue to expand indefinitely. However, this is not certain. Our observations are still very limited. Since most of the universe is unobservable, the true nature of vacuum energy remains shrouded in mystery. It may exhibit different behaviors in unobservable regions, or perhaps what we see is only a small part of a larger system, so even if vacuum energy appears to be constant, it may actually have a variable structure. In short, vacuum energy is not just the fullness of emptiness. It is the compass that determines where the universe is headed over time. Without understanding it, we cannot comprehend the beginning or the end of the universe. This energy is both invisible and affects everything. And with this characteristic, it is perhaps the most fascinating mystery of the physical world. 34. What did the void look like in the first moments of the universe? When we think about the first moments of the universe, the image that comes to mind is usually a big bang, followed by a sea of chaos, heat, and light. However, this visual is meaningful within the framework of classical physics. From the perspective of quantum physics, however, the first moments of the universe are not described as emptiness, but as an incredibly dense energy environment where all fields are active at the same time. In this case, what we call emptiness was actually a structure where quantum fields overlapped and no particles had yet stabilized. We are talking about a moment when matter, energy, and even time were not yet defined. The universe was governed by quantum gravity during the Planck time, approximately 10 to the negative 43rd seconds. During this time interval, space-time does not exist in the classical sense. It is a foamy, constantly changing structure. Therefore, even emptiness is not a clear concept. Space behaves more like a quantum instability. Fields collide with each other, vibrate, create, and destroy temporary particles. The Higgs field has not yet stabilized, so particles are massless. Even light does not behave in the classical sense in this environment. In other words, this space is like a kind of raw material of existence, where all potential is intertwined. In these first moments, an incredible symmetry reigns in the universe. These symmetries break down over time. As a result of these breaks, particles are formed, forces separate, and the first seeds of matter are sown. This transition process also redefines the state of the fields. With the stabilization of the Higgs field, the universe reaches the type of emptiness we first recognize. But even this is not absolute emptiness. In other words, the initial emptiness of the universe is not the same as the emptiness we see today. One carries creative potential, while the other is its result. Therefore, the void in the first moments of the universe is not actually a void. It is an energy chaos in which everything is hidden. As modern physics tries to understand this chaos, it may be seeking answers not only to how the universe came into being, but also to why it had to come into being. And this answer lies hidden in the structure of the void. 35. Is the void truly constant, or does it change over time? According to traditional thinking, space is seen as a fixed and unchanging background. That is, space itself is a static, passive stage. Events occur within it, but it remains unchanged. However, quantum field theory and cosmology present us with a completely different picture. Space is not actually stationary. It is constantly in motion due to quantum fluctuations, and these movements produce physical results, even at the microscopic scale. Furthermore, the structure of space can change over time. This is because space is not merely a passive backdrop for existing fields. It is the energetic state of those fields, and this state may be evolving along with the expansion of the universe. The space that existed in the early universe is not the same as the space we know today. In the early universe, there was a vacuum state with higher energy levels. This high-energy vacuum caused the universe to expand rapidly during the inflationary period. During this process, space behaved like a phase transition, releasing its energy outward, and the universe transitioned to its current low-energy vacuum state. Such a change suggests that space can evolve over time. In other words, when we think of space as an energy sea, its internal structure can undergo phase transitions similar to the vaporization and condensation of water, and the effects of these changes on the universe can be enormous. In some cosmological scenarios, even the current vacuum may not be permanent. A state known as a metastable vacuum is discussed. If the vacuum we currently inhabit is not the true lowest energy state of the universe, a transition to a lower energy vacuum could occur one day. This would mean that all physical laws and particles would change. Such a transition would occur at the speed of light and erase the entire universe from end to beginning. Though it may sound like the end of the world, this scenario demonstrates that space is not static and contains a form of quantum potential. Therefore, what we call space is not a static field, but a dynamic formation with an internal structure that can evolve over time and even determine the fate of the universe. Understanding it is equivalent to understanding the change of time and matter. Perhaps space is the real protagonist of the universe. It forms the basis of everything, not only with its invisibility, but also with its variability. I would like to make a small reminder. If you would like to support me, you can access exclusive content by clicking the Join button at the bottom of the screen. Your support is really valuable to me. Thank you in advance. Let's continue with our video. 36. Why is there energy where there is nothing? This question challenges our most fundamental intuitions in physics. If there is nothing, then there should be nothing, right? However, quantum mechanics overturns this intuition. According to quantum field theory, even an environment with no particles is not completely empty, because even in a vacuum, energy levels cannot be reduced to zero. This is called zero-point energy. This energy is inevitable due to Heisenberg's uncertainty principle, because physical quantities such as position and momentum cannot be measured precisely at the same time. This means that the energy of a field can never drop to exactly zero. There is always some fluctuation remaining. This zero-point energy causes virtual particles to constantly form and disappear in a vacuum. These are quantum entities that do not exist in the classical sense, but momentarily affect the energy level. These transient particles exist for such a short time that they cannot be measured, but their existence produces measurable results. For example, experimentally verified phenomena such as the Casimir effect demonstrate that there is indeed energy in empty space. When two plates are placed very close to each other, the vacuum energy between them changes, causing the plates to be attracted toward each other. This is a vivid proof that empty space is not nothing. Additionally, this energy influences the expansion of the universe. When zero-point energy is associated with the cosmological constant, it could serve as a propulsive force capable of sustaining the expansion of space itself. In this case, even in a place where nothing exists, there is not just energy, but a dynamic force that determines the fate of the universe. Thus, space is actually the most concentrated form of potential. Although it is physically invisible, its effects are everywhere. It plays a role at every level, from subatomic particles to galaxy clusters. In conclusion, There's no such thing as a place where nothing exists, because even nothing is something at the quantum level. The laws of physics are structured in such a way that even space is an active energy field. Perhaps this is why the universe exists, because in the true sense of the word, nothing is not possible. The secret of existence may lie precisely in this paradox. 37. Could space be a field of information? One of the revolutionary ideas that emerged with quantum physics is that information is a fundamental element of nature. In traditional physics, matter, energy, and fields were at the forefront. However, in the quantum world, information is seen as a factor that shapes physical reality itself. In this context, could space be more than just a place filled with energy? Could it also be a field containing information? This question is not merely speculative. It also carries profound implications for fundamental physics and information theory. Because if space is a carrier of information, it would require a completely different understanding of how the universe operates at its most fundamental level. Quantum entanglement experiments show that information can be transferred between two particles, regardless of the distance between them. This suggests that the space between them is not merely a passive gap. If information is related to the state of a particle, and this information can reach another particle through space, then space itself could be a type of carrier for this information. Furthermore, in some models such as string theory, space-time itself is defined as a information processing structure. In other words, space is not just energy and field, it's also a fabric that contains information. The holographic principle also supports this idea. According to this principle, all physical information within a region can be encoded on the surface at the boundary of that region. So the entire universe could be encoded as information on a two-dimensional surface that appears three-dimensional. This suggests that space is a structure filled with information. Because if space-time itself contains information, then what we call space is a plane saturated with information. Therefore, it is no longer sufficient to think of space as a silent, neutral, and inert field. Perhaps space is an invisible system that forms the information infrastructure of all events in the universe. Just like the codes behind the images on a computer screen, the invisible codes of information may lie behind everything we see in the universe. From this perspective, space is not the physical, but the logical foundation of the universe. 38. Could the energy of space be the same thing that inflates the universe? The inflation process, believed to have occurred in the early stages of the universe, is a revolutionary concept in cosmology. During this process, the universe expanded by 1 trillion times, and did so in an incredibly short amount of time, in a fraction of a billionth of a second. The source of this expansion is believed to be a mysterious form of energy, the inflaton field or vacuum energy. At this point, a striking idea emerges. Could the dark energy that is currently causing the universe to expand at an accelerating rate be the same energy that drove that initial inflation? If so, vacuum energy could be providing the driving force for expansion, just as it did at the birth of the universe. This means that space is not just the master of the past, but also of the present and the future. According to inflation theory, space was filled with energy, but this energy had a constant value and had the power to stretch space-time. This constant energy created negative pressure, causing the universe to inflate. The same principle applies to what we now call dark energy. Dark energy is also a form of energy evenly distributed throughout space-time and creates negative pressure. In this sense, the energy of the void may have driven inflation in the past and is now driving accelerated expansion. In other words, we are witnessing the same fundamental force manifesting itself in different forms at different times in the universe. If this scenario is correct, vacuum energy is more than just the building block of the universe. It is the cosmic pen that writes its destiny. Because this energy does not merely trigger expansion. Over time, it could also determine the universe's end. If this energy remains constant, the universe will continue to expand indefinitely. But if it changes, for example, if the vacuum is in a metastable state and transitions to another energy level, the entire universe could face sudden and inevitable annihilation. This makes vacuum energy not just a spark of creation, but also a potential final curtain. Such a perspective suggests that space is not merely a stage, but the lead actor who initiates, sustains, and when necessary, concludes the play. The energy inherent in space determines the cosmic destiny of the universe. Perhaps what we call the universe is a ripple formed within the void, a temporary, vibrating bubble. And the story of this bubble is written in the energy of the void. 39. Why is there something rather than nothing in the universe? This is one of the oldest and most challenging questions in both philosophy and physics. Why is there something rather than nothing? Why does the universe exist? The assumption underlying this question is that nothingness seems more natural because existence is complex and requires an explanation. However, quantum physics challenges this intuition because the laws of physics show us that nothing is not a completely stable state. Nothingness, if it is truly possible, could be an unstable state. The quantum vacuum, by its very nature, is constantly fluctuating. These fluctuations prevent energy levels from settling at zero. In other words, the laws of physics require that something exists even in a vacuum. Furthermore, some physicists have proposed the universe from nothing scenario. This idea suggests that the universe could have emerged from absolute nothingness, a state in which time, space, particles, and even the laws of physics do not exist. In this case, the existence of the universe is not attributed to an external cause, but to spontaneously arising quantum fluctuations. Just as virtual particles suddenly appear and disappear in a vacuum, the universe itself may have emerged as a quantum fluctuation. This explains the existence of the universe not as a necessity, but as a probabilistic outcome. Additionally, there are theories suggesting that the total energy of the universe is zero. While matter and energy have a positive total, gravity produces negative energy. These two types of energy can balance each other out. If the total energy of the universe is truly zero, then the idea of a universe from nothing gains further meaning. Because the emergence of a system with zero energy is physically possible and even inevitable. Thus, the universe is both something and a natural extension of nothingness. This idea shows us that nothingness is not as static or normal as we might think. On the contrary, nothingness could be an impossible, unsustainable state. The laws of physics seem to require that something exists, and the universe may be the inevitable result of this necessity. Perhaps this is the reason for the existence of the universe, that nothing cannot exist. This may be the deepest paradox. 40. Could quantum fields be a universal consciousness? This question directly challenges the boundaries of science, but also opens the door to metaphysics. Quantum fields are considered the fundamental structures behind every particle in the universe. Fundamental particles such as electrons, photons, and quarks are nothing more than vibrations in these fields. In this case, the entire universe is a function of these fields. But are these fields purely physical, or could they also possess a consciousness-like quality? If the fundamental structure of the universe is these fields, and these fields influence existence at every point, could we then conceive of quantum fields as a kind of universal consciousness? This view is not a mystical fantasy, but a serious idea explored by some scientists and philosophers. A philosophical movement called panpsychism argues that consciousness is a fundamental property of matter. In other words, there may be sparks of consciousness in everything from atoms to galaxies in varying degrees. In this case, quantum fields would not only possess physical properties, but also contain a kind of perception or internal experience. In this model, where all fields are fundamental, consciousness also becomes a kind of field, and this field continues to exist at every point in the universe. Quantum fields interact with each other and can establish simultaneous connections, even over long distances, through phenomena such as entanglement. This connection can be compared to the non-local nature of consciousness. Human consciousness cannot be reduced to a specific region of the brain. It is a holistic process. Similarly, the consciousness of the universe may not be located in a specific region, but rather in the intertwined nature of all quantum fields. This idea suggests that the universe itself is a kind of mega-organism, and that consciousness is its natural consequence. This kind of understanding stands at the intersection of science and philosophy. Of course, these ideas cannot be experimentally tested today. However, the idea that the quantum fields underlying physical reality carry a universal potential for consciousness could completely transform our view of the universe and ourselves. Perhaps the universe is not merely a mechanical contraption. It is an entity that experiences, learns, and evolves, and we are the bubbles of consciousness within it. 41. Is dark energy really empty space or something else? Dark energy is accepted as a mysterious force that accelerates the expansion of the universe. However, there is great uncertainty about what it is, or even what it resembles. Many theories define dark energy as vacuum energy, or the energy of emptiness. Quantum theory tells us that emptiness is not actually empty, but filled with constantly fluctuating energy fields. However, things get complicated when cosmology enters the picture. This is because there is a huge discrepancy between the amount of vacuum energy calculated theoretically and the amount of dark energy measured observationally, approximately 10 to the 120th power. This historical discrepancy is referred to as the greatest calculation error in the history of science. This discrepancy raises deep doubts about whether dark energy is truly vacuum energy. Perhaps dark energy has a nature that is very different from what we imagine. For example, some theories propose a dynamic field called quintessence. This field changes over time, behaves like a fluid, and is different from classical vacuum energy. On the other hand, some physicists suggest that dark energy may be an unknown property of space-time embedded in its geometry. In this case, the expansion of the universe may not be a direct product of empty space, but rather stem from a deep structure inherent to the universe itself. Alternatively, dark energy may be related to the multiplicity of the universe. If multiple universes exist and we are only in one of them, dark energy could be one of the special conditions of our universe. Other universes may have different physical constants, and dark energy may either not exist or be very different there. This leads us to explain dark energy not with the vacuum, but with cosmic randomness. In other words, dark energy may not be the result of emptiness, but rather a lucky outcome of our universe. With so many possibilities, it is currently impossible to definitively answer whether dark energy is emptiness or not. However, one thing is clear. This mysterious energy is shaping the destiny of the universe, and the nature of this energy could fundamentally change how we understand space, and therefore how we define existence itself. Perhaps dark energy is not a whisper within space, but an echo that transforms space itself. 42. If space is actually something, what does nothing mean? In traditional thinking, nothing means absolute nothingness. There is no matter, no energy, no time, and no space. However, modern physics fundamentally challenges this idea, because according to quantum theory, even emptiness is filled with energy and behaves actively. Emptiness becomes a kind of foundation for existence. In this case, the real paradox is this. If emptiness is something, then what exactly is nothing? Perhaps nothing is just a conceptual phantom, an abstraction with no counterpart in physical reality. The problem behind this question is the inadequacy of our language. What do we actually mean when we say nothing? From the perspective of quantum physics, it is impossible to create absolute emptiness. According to Heisenberg's uncertainty principle, energy levels cannot be fixed at zero. In other words, even in the quietest environment, quantum fluctuations occur. This transforms emptiness from a nothingness into a potential source of everything. Thus, physically speaking, nothing may be an unattainable ideal, perhaps even non-existent. Philosophers, however, approach this concept differently. Ontologically speaking, nothingness means the complete absence of existence. However, this kind of absence cannot even be conceived by a conscious mind, because even thought is dependent on existence. In that case, the idea of nothing is a concept that only makes sense when compared to existence. In other words, nothing is actually the absence of something. It is not an entity in itself, but the definition of non-existence. Therefore, nothing may be a philosophical illusion that has never existed. Quantum theory not only shows us emptiness, it also declares that emptiness is full. Emptiness is the beginning of reality. It is not the source of something, but the source of everything. From this perspective, there is no such thing as nothing, only states that have not yet become something. 43. Can nothingness itself be a type of energy? Although this question may seem paradoxical at first, it becomes quite meaningful when considered within the framework of quantum physics. This is because nothingness is not absolute absence in quantum field theory. Quantum vacuum is in a state of constant fluctuation, even when nothing appears to exist. These fluctuations cause virtual particles to form and disappear, a phenomenon known as vacuum energy. Vacuum energy is the idea that emptiness possesses its own unique form of energy. This leads us to the striking conclusion that nothingness itself could be energy. This energy is different from ordinary forms of energy. It cannot be directly measured with the human senses, like energy in thermodynamic systems. However, its effects can be observed on the largest scales of the universe. Cosmic expansion. The ever-increasing speed at which the universe is expanding is seen as strong evidence for the existence of this form of energy. The ironic point here is this: the thing that exerts the most powerful influence on the structure of the universe is, in appearance, nothing. This energy, which we cannot see or directly perceive, is pushing galaxies apart. In this case, we may need to view space as an energy field. Just like electric or magnetic fields, space could be a medium that carries energy. This perspective radically changes our understanding of reality. Perhaps energy is not merely a property of matter. Perhaps emptiness, or apparent nothingness, is the fundamental form of existence itself. In other words, energy is not inherent in matter, but in emptiness. Nothingness itself may be the power behind the universe. This thought leads us not to mysticism, but to scientific wonder. Perhaps the universe is a manifestation of the energy of nothingness. Everything has emerged from what appears to be nothing, but that nothing was precisely the potential within everything. This is where physics meets philosophy, where reality negates itself in order to exist. 44. Why do quantum fields continue to exist even in empty space? In quantum physics, the concept of space does not refer to a completely empty area as in classical physics, but rather to a constantly moving and potential-filled ground. Quantum fields exist in this ground and are present at every point in space. So whether there is a particle or not, the space of the universe is made up of these fields. Fields such as the electron field, the quark field, and the Higgs field are spread throughout the entire universe and, in a sense, form the fabric of existence of the universe. No matter where you go, whether you are at the center of a star or in the most desolate void between galaxies, these fields are still there. What forces them to exist, even in a vacuum, is that they are not physical entities, but fundamental mathematical entities. They are universally valid by the laws of nature. The fact that these quantum fields constantly carry vibration potential, even in empty space, explains why the universe appears to be a dynamic and constantly changing structure. A particle is a vibration of these fields. In other words, the emergence of something is actually the vibration of a field that was already there. Therefore, the field exists even in empty space, because the existence of the field is not dependent on particles. On the contrary, particles are its result. Quantum field theory defines empty space as a medium that is devoid of matter, but filled with potential. For this reason, empty space is a true starting point. It is not nothingness, but a field of existence filled with unlimited possibilities. This is why quantum fields remain unchanged throughout time and space. They operate at the most fundamental level of existence, much like universal constants. In a sense, the physical universe is like a stage built upon these fields. Particles, forces, and all interactions are determined by the behavior of these fields. Without these fields, there would be neither matter nor force. Because these fields continue to exist even in the void, there is always a possibility of movement in the universe. This idea reveals why the void is never completely empty. The void, together with the fields it carries within itself, is the hidden carrier of reality. The void, which appears silent and dark, is actually the deepest and most constant pulsation of the entire universe. Even in places that appear to be nothing, Quantum fields vibrate as if waiting for a song to be played. 45. If the entire universe is energy waves floating in space, what are we? If the universe really consists of quantum fields and the energy waves they create, then all beings, including humans, are organized forms of these waves. It is no longer sufficient to explain our existence with material particles. We are organized patterns of energy fields. Even an electron is actually a vibration in the electron field. Similarly, our brain, our thoughts, and our consciousness are the result of the extraordinarily complex interactions of these fields. In other words, we are a conscious organization that exists thanks to the dance of waves in the void. The knowledge that the universe is filled with emptiness redefines us as wave beings rather than material beings. This forces us to rethink not only the physical level but also the existential level. If everything is a form of energy waves, then the boundaries between us may also be an illusion, because quantum fields are spread throughout all of space. Even though there appears to be an atomic void between us, this void is actually just different vibrations of the same field. We are not separate, but different folds of the same fabric. This idea can help us set aside individuality and understand universal wholeness. We may be the universe's attempt to explain itself to itself. However, none of this makes our existence any less real. On the contrary, it elevates us to a deeper and more profound position. We are the conscious eyes of the universe, where vibrations from the void merge with awareness. When we look at galaxies with our eyes, the universe is actually looking at itself. When we think, the energy echoing through the void transforms into thought. We may have been born from the waves of quantum fields, but these waves are a symphony carrying infinite possibilities within them. And we are the short but meaningful melodies of that symphony. Perhaps that is why when we look at the universe, we see not a beginning, but a continuity. Because if even emptiness is not empty, then everything is an eternal movement of existence. We are the spark of that movement that has become aware of itself. The invisible waves within quantum fields have found consciousness in us, turned into questions, and finally asked themselves, what is there where there is nothing? When we learn that emptiness is not truly empty, we begin to perceive the invisible yet powerful structure beneath the surface of the universe. Quantum fields, virtual particles, vacuum energy, dark forces, all of these tell us, even where there is nothing, there is actually something. Perhaps nothingness is the universe's own illusion, and we are the small but conscious sparks of this infinite potential. The background we perceive as the universe's emptiness is actually existence itself. Understanding the invisible may be the purest form of confronting existence, because the question itself, as well as the one who asks it, is a miracle born from the universe. If you enjoyed this journey, don't forget to like the video, leave a comment, and subscribe to our channel. With your support, we can grow this community full of science and discovery. Share your thoughts with us, because discovering the unknown together is always more exciting. As Carl Sagan once said, reality is probably stranger than we think it is. Science is the most powerful tool we have to understand that strangeness.